Let's continue our discussion with a look at engine-out maneuvers. We'll begin with takeoff considerations. An engine failure during departure requires a rapid assessment of the situation and immediate action. Evaluating the options before takeoff makes your decisions much easier. For example, always compare the density altitude with your airplane's single-engine service ceiling. If you fly when the density altitude exceeds this ceiling, you may have no option but an off-airport landing should an engine fail. However, you can improve the situation by waiting for better conditions or making the flight with less fuel, passengers, or baggage. You should also make sure that the accelerate stop distance for the existing conditions is not longer than the available runway. Just before takeoff, review the procedures and airspeeds to follow in case of engine failure. This includes a plan of action to avoid obstacles if your climb performance is suddenly reduced. Always know what your airspeed, altitude, and configuration must be for you to continue the takeoff after an engine failure. If an engine failure occurs on the takeoff roll below VMC, the airplane will immediately turn toward the failed engine. Your only choice is to close both throttles to maintain directional control and abort the takeoff. If an engine fails just after liftoff, you must make an immediate decision whether or not to continue. If you have not begun to retract the gear and there is enough runway remaining, close the throttles and land. If you decide to continue the takeoff, you must maintain positive control of the airplane and accelerate to VYSE. If there are obstacles to clear, accelerate to VXSE. Either of these may require a momentary descent. Make sure the engine controls are set for maximum power, and once you have a positive rate of climb, reduce drag by retracting the gear and flaps according to the manufacturer's recommendations. Make sure you've identified and verified the failed engine, and shut it down. Remember that this procedure is only a typical example. You must perform the exact sequence of steps given in the pilot's operating handbook. During the climb, maintain VYSE and keep 5 degrees of bank toward the operating engine. Even if you can't establish a climb, you should maintain VYSE since that will give you the slowest rate of descent and allow you the most time to prepare for an emergency landing. While an engine failure during the en route phase of flight may not be as serious as at takeoff, you should still apply full power to conserve altitude while you take care of the situation. Once you've identified and verified the inoperative engine, try to determine the reason for the failure and restart the engine if practical. If you can't restart the engine, use the checklist in your pilot's operating handbook to shut it down and feather the propeller. Once you've done all the checklist actions, you should head to the nearest suitable airport and land. Remember that the airplane will fly best if you maintain 5 degrees of bank toward the good engine and use trim to relieve the control pressures. You should maintain altitude if at all possible. However, if the engine fails while you're cruising above the single-engine service ceiling, you'll have to descend at VYSE to that ceiling. This is particularly significant if you're over high terrain. Obviously, your pre-flight planning should include reviewing areas of lower terrain and the locations of alternate airports. Remember, descending at VYSE gives you the slowest rate of descent and conserves altitude for the longest time. For a long flight, use the fuel cross-feed system on the aircraft to maintain fuel balance. You especially want to avoid having a heavier fuel load on the same wing as the failed engine. As you get close to the airport, plan for the approach and landing well in advance and fly a stabilized descent to the traffic pattern. Maintain the airspeed at or above VYSE throughout the pattern until the landing is assured. You may want to fly a larger pattern to allow for shallower turns and better visibility. Do not lower the landing gear until the landing is assured. Delay lowering any flaps until the gear is down and you are absolutely certain of making the runway. Remember that as you decrease power on the good engine during the flare, the yawing tendency you've been correcting for will decrease. So be positive with your control inputs to keep the airplane straight down the runway on the rollout. One of the most important reasons for planning your engine-out approach thoroughly is to avoid the need to make a rejected landing. Under certain conditions of airplane weight and density altitude, this maneuver may not be possible. Part of your approach planning should include a go, no-go altitude for a rejected landing based on airplane performance, obstacles, and terrain. If a go-around becomes necessary, make your decision as early as possible. Carefully add full power on the operating engine, and smoothly raise the nose to establish a shallow climb. Reduce drag by raising the flaps and landing gear, and accelerate to VYSE. Once again, follow the specific procedures outlined in your pilot's operating handbook. The last maneuver we'll discuss is officially known as engine inoperative, loss of directional control demonstration. It is one of the most important maneuvers you will practice in your multi-engine training. This maneuver shows you how to maintain directional control with an engine inoperative, and the procedures to follow when directional control cannot be maintained. As with other multi-engine maneuvers, 3,000 feet AGL is the minimum altitude for performing and recovering from this demonstration. The proper configuration for the demonstration is with the propellers set to high RPM, the landing gear retracted, both the wing flaps and cowl flaps at the takeoff setting, and the trim set for takeoff. Establish the airspeed at VYSE and reduce the power on the critical engine as recommended by the manufacturer. Smoothly increase the pitch attitude to bleed off airspeed as you add climb power to the operating engine. Establish a 5-degree bank toward the operating engine and maintain the heading with rudder pressure. As the airspeed decreases, you will eventually reach a point where full rudder is not effective enough to maintain the heading. As soon as this happens, recover by simultaneously reducing power on the operating engine and decreasing the angle of attack. As you regain directional control, complete the recovery by slowly increasing power on the operating engine and establishing the airspeed at VYSE. In some cases, a high-density altitude may keep you from performing this maneuver. The reason for this is that the calibrated stall speed of an airplane remains the same regardless of altitude. The VMC published in the Pilot's Operating Handbook is established at sea level. But as altitude increases, the actual VMC decreases because the operating engine is developing less power. Above a certain density altitude, the actual VMC is less than the stall speed, and you will start to get indications of a stall before you lose directional control. In this situation, the demonstration should not be attempted. Having one engine at idle and the other at full power as you approach a stall is extremely hazardous. This is one of the reasons you should always have a qualified instructor on board when practicing this maneuver. Up to now, we've only talked about visual maneuvers. In the next section, we'll cover instrument flight in a multi-engine airplane. Instrument flying in a multi-engine aircraft is basically the same as in a single-engine airplane. The main differences relate to the potential for an engine failure, the higher operating speeds, and the more complex systems installed in these aircraft. If you're instrument rated when you apply for your multi-engine rating, you must demonstrate instrument proficiency during the practical test or have your multi-engine privileges limited to VFR flight. During the instrument portion of the flight test, you'll demonstrate the procedures for an engine failure in straight and level flight and turns. You'll also make an instrument approach with both engines running and an approach with one engine inoperative. Let's begin with a look at how to recognize an engine failure by instrument reference. The attitude indicator and heading indicator show a roll and yaw toward the failed engine, while the ball in the turn and bank indicator deflects toward the operating engine. Once you've recognized an engine failure, set the engine controls for maximum power, reduce drag, identify and verify the failed engine, and feather the propeller. The distraction of securing a failed engine and the unequal in-flight forces makes it imperative that you cross-check the flight instruments to maintain aircraft control. Once you're stabilized in the engine-out configuration, use trim to help you maintain the precision required in instrument flight. Hold 5 degrees of bank toward the good engine to improve your heading control and straight and level flight. And remember that the ball will be slightly off-center toward the operating engine. When making turns, use a standard rate turn for best performance. The next maneuver we'll discuss, an instrument approach with both engines operating, is flown with the same established procedures you've used in single-engine aircraft. You already know that an instrument approach requires several tasks to be performed in a relatively short time. The higher approach speed and more detailed checklist procedures of a light twin increase your workload. Good cockpit management and anticipating situations to stay ahead of the airplane makes multi-engine approaches much easier. In some cases, the higher approach speed may put you in a different approach category than you've used in a single-engine airplane. If you're in a situation where you have to fly an instrument approach with an engine inoperative, do everything you can to ensure that your first attempt will be successful so a missed approach will not be necessary. If at all possible, fly the approach to an airport that has weather well above the approach minimums. Fly a precision approach if one is available, since it gives you a constant rate of descent down to the runway. A non-precision approach may require you to maintain level flight at low altitude with a high power setting on the good engine. If radar service is available, request vectors as soon as possible. This reduces your workload and usually results in less maneuvering during the approach. Don't hesitate to advise the controller of your emergency situation so you can get traffic priority. When flying the actual approach, use normal procedures as much as possible. Deviating from a familiar routine can cause confusion and lead to an item being skipped. When you're established inbound on the final approach course, slow down to approach speed, or VYSE, whichever is higher. Maintain this throughout the approach until landing is assured. If sufficient power is available, lower the landing gear at the final approach fix to begin a stabilized descent down the glide path. If power is not available, lower the gear when you're sure you can make the runway. Flap extension is the major deviation from normal procedures. Use the minimum flap setting recommended by the manufacturer until you're certain of making the runway. Once you have the runway in sight, plan the final segment of the approach for a gradual power reduction so you can touch down with the good engine at or near idle. Remember that this and all other procedures in this presentation are general in nature. Always refer to your pilot's operating handbook for the actions to follow for each situation. Learning to fly a twin is an exciting and challenging experience. A multi-engine rating gives you greater versatility and adds a sense of professional accomplishment to your flying career. It's important to remember that each twin has its own operating limitations and flight characteristics. A thorough understanding of your airplane adds to the overall safety of each flight.